Hello, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I'd do differently. Today, we're going to be getting into authorization and role level security, server actions, role level security, and least privilege. Let's get into it. Authentication tells your system who is making a request. Authorization tells your system what the person is allowed to do. There are different questions with different enforcement mechanisms for each one of those, and a failure in authorization is often worse than a failure in authentication. Here's why. A failed authentication means an attacker can't log in. A failed authorization means an attacker who was logged in, possibly with a legitimately obtained account, can access data that doesn't belong to them. In an e-commerce platform, that means reading other users' orders, seeing their purchase history, accessing their payment methods. The insecure direct object reference vulnerability, IDOR, is one of the most common vulnerabilities in web applications, and it's purely an authorization failure. The user is authenticated. The system just didn't check whether they're allowed to access that specific resource. This video is about how I enforce authorization on my platform using 3 independent layers: application level checks in the server actions, role level security at the database layer, and a key strategy that ensures the client can never bypass RLS regardless of what code runs in the browser. Let's get into it. So, authentication versus authorization. These are different questions enforced at different points. Authentication asks, who are you? It produces a verified principal, a user ID the rest of the system can trust. Supabase Auth produces a JWT with a user ID. Middleware verifies that JWT on every request. After authentication, I know the user ID is valid, nothing else. Authorization asks, what are you allowed to do? Given a verified identity, it determines which resources and operations are permitted. I enforce this at 3 points. In my platform, a logged-in user is authenticated. Being authenticated doesn't mean they're authorized to read another user's order. The JWT tells me who they are. Authorization tells me what they can do. The practical implication of this: authentication and authorization are separate code paths with separate bugs. A bug in authentication doesn't create an authorization hole. A bug in authorization doesn't require circumventing authentication. An attacker with a legitimate account purchased with a stolen credit card or just registered can exploit authorization vulnerabilities without ever breaking authentication. We're going to be talking about IDOR. The most common authorization failure in web applications is, in fact, insecure direct object reference. The code on the left shows the pattern. A route handler fetches an order by its ID from the URL parameter. No authorization check. Any authenticated user can request any order ID and receive the data. To access another user's order, you just guess or enumerate order IDs. With UUID primary keys, enumeration is hard, but not impossible if you observe your own order IDs and probe similar values, or if you find the ID exposed elsewhere. The reason this happened is because the developer verified authentication. The user is logged in and assumed that was sufficient. But being logged in doesn't mean you're allowed to access every resource in the system. Here is a correct mental model. For every request involving a resource ID, ask, does the authenticated user own or have explicit access to this specific resource? For orders, does this order belong to the current user's ID? For admin operations, does this user's role grant admin access? This check must happen before any data is returned. Every time, without exception, RLS makes without exception structurally guaranteed. The database enforces it regardless of what the application code does. Role level security. Role level security is a Postgres feature that adds an authorization predicate to every query against the table. When RLS is enabled on the orders table with the policy using auth ID is user ID, every query against orders automatically gets the where clause appended. Select all from orders becomes a select all from orders where user ID is the auth UID. This happens at the database layer. It's not application code. It's not middleware. It's not a convention. It's enforced by Postgres on every query, regardless of how the query was constructed or which code path was sent. Auth UID is a function provided by Supabase that extracts the user ID from the JWT in the current request context. The database calls this function, gets the current user's ID, and uses it as the filter. No application code is involved in producing that value. The consequence of this, a developer who forgets to add where user ID is set to user ID to a query doesn't create an IDOR vulnerability. RLS adds the filter anyway. The only way to bypass RLS is to use the service role key, a separate credential that lives only in the server-side code, never in the browser. 3 steps to set up RLS: enable it on the table, create policies for each operation, and know the gotchas. First, alter table orders enable row level security. This enables RLS but doesn't add any policies. Table with RLS enabled and no policy denies all access. Every query returns 0 rows. This is the safe default, but it's easy to mistake for a bug. For an orders table, a select policy using auth ID, user ID, right, means users see only their own orders. An insert policy using with check auth UID is set to the user ID, prevents users from creating orders on behalf of other users. An admin policy using is admin auth UID lets admin users see everything. Here are 4 policy gotchas. Using versus with check. Using filters which rows are visible for select and update, which rows can be seen or modified. With check validates what can be written for insert and update. It also validates what values are allowed on the row being created. No policy means everything is denied. Enable RLS without adding policies and every query returns 0 rows. Multiple policies for the same operation combined with, or if either policy grants access, the row is returned. The goal is to keep policy simple. Auth UID is assigned the user ID, right? Or it's equivalent to the user ID, is an index lookup, and is effectively free. Subqueries and joins in policies are measurable overhead to every query. So we have 3-layer defense. My authorization system has 3 independent layers. Each catches a different failure mode. Removing any one creates a vulnerability the others don't cover. The first layer is server action check. Application level: is the user authenticated? Does their role allow this operation? Verified before any database call. Catches unauthenticated calls, role mismatches, and business logic violation. The second layer is RLS policy. It's at the database level, and the main questions are: does this user own this specific row? It's enforced on every query regardless of application code path. This catches IDOR bugs when the server action forgets the ownership check, missing where clauses, and direct SQL access via the Supabase dashboard, and migration script accidents. Now, the third layer, anon key only. No service role key in the browser or the client side code. The service role key bypasses RLS entirely. It exists only in server-side environment variables and is used only in server actions that have already verified the user's role. The client can never bypass RLS because it doesn't have the credential would allow it to. This catches code that accidentally skips RLS, compromised client-side code, and cross-site scripting attempts at direct database access. We're moving on. Authorization in server actions. The order of operations in a server action matters for both correctness and security. With wrong order, the data is read first, then checked whether the user owns it. Even without RLS, this means the data was fetched from the database before the check ran. In a race condition, the response might be partially formed before the check fires. And conceptually, you're working with data you shouldn't have retrieved. And for the correct order, you verify authentication first, then query with the user ID filter included, then check the result. and return not found rather than forbidden when the record does not belong to the user. Not found does not confirm whether the resource exists. Forbidden does. The belt and suspenders pattern. Server actions include .eq user, here, in the query explicitly, right? The belt in the query explicitly. RLS adds the same filter at the database layer. That is the suspenders. If the server action has a bug and omits the user ID filter, RLS catches it. If RLS is somehow misconfigured for this table, the server actions explicit filter catches it. Both must fail simultaneously for data to leak. Least privilege means every code path has only the permissions required for its specific operation. 3 credential levels in my platform. The anon key lives in the browser and client-side code. It enforces RLS on every operation. It reads return only what RLS permits. Its rights are validated against RLS policies. It cannot bypass RLS. The service role key lives in server action and server-side scripts. It bypasses RLS entirely. It's used only after explicit role verification. Admin-only server actions verify the user's role. Then use the service role client to perform operations that require accessing other users' data. They never expose this key to the browser. The database URL is used only in Supabase CLI for migrations, never in application code. A practical rule to follow is the anon key is the default. Use the service role key only when you need to bypass RLS in admin operations that have already verified the user's admin role. The service role key in a server action that hasn't verified the user's role is just as dangerous as no authorization at all. The authorization error is what to return. The error code in your API returns reveal information to attackers. Wrong choices leak data. When a user requests a resource that doesn't belong to them, this returns a 404 not found, not 403 forbidden. 403 confirms the resource exists. An attacker probing order IDs learns which IDs are valid by looking for 403 responses and knows the rest are missing. 404 for both doesn't exist and exists but not yours makes the two cases indistinguishable. When an unauthenticated user requests a protected resource, 401 unauthorized, not 403 forbidden. 401 signals try authenticating. 403 signals authenticated but not allowed. Use the correct signal. When an authenticated user attempts an admin-only operation, 403 forbidden with a generic message. Never reveal which role would be sufficient, just that current role is insufficient, and never silently degrade. Returning a partial or empty response without an error code hides the authorization failure from monitoring. So testing authorization, what actually matters. Authorization bugs don't appear on the happy path. They appear on the adversarial path. When a user tries to access something they shouldn't, the tests that find vulnerabilities deliberately try to break the authorization model. So here are 5 test categories, right? Cross-user access. This creates 2 users, log in as user A, attempt to access user B's orders and profile, assert every attempt, returns 404 or 403. Unauthenticated access. Call every protected endpoint without a session token. Assert every call, returns 401. Privilege escalation. As a regular user, attempted admin operations. Delete a product, read another user's profile, etc. Assert all, return 403. Direct RLS test. Using the anon key directly, run SQL queries that should be restricted. Assert they returned 0 rows, not an error. ID enumeration resistance. Attempt to access resources with sequential or guest IDs while authenticated as a non-owner. Assert 404 for all. Verify no timing difference between not found and not yours. Timing differences can reveal resource existence. Run these tests against the real Supabase database. RLS is what you're testing. Mocked database clients don't exercise RLS. Authorization is not a single check. Authentication answers, who are you? Authorization answers, what are you allowed to do? They are enforced at different points. A logged-in user is not automatically authorized to access every resource. RLS adds the authorization predicate at the database layer. Structurally, but not by application convention, a developer who forgets to add a where clause doesn't create an IDOR vulnerability when RLS is enabled. We have the 3 layers: server actions, the application check, and RLS, the database enforcement, as well as the anon key only. There's no bypass credential on the client. Each catches a different failure mode. Remove any one and you have a gap. Belt and suspenders. Server actions add user ID filters explicitly. RLS adds it again at the database level. Return not found, not forbidden for unauthorized resource access. Don't confirm resource existence. We test the adversarial path. Cross-user access, unauthenticated calls, privilege escalation, direct RLS queries with the anon key. The happy path tests your code. The adversarial path tests your security. For client, authorization on this platform is enforced at 2 independent layers. Server actions verify user identity and ownership before any database call, and row-level security enforces the same rules at the database layer for every query. The client uses the anon key only. It cannot bypass RLS regardless of what code runs in the browser. I'm Fleshed Out Thoughts. I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing authorization for your own platform, RLS Policies, 3-layer defense, or the adversarial test suite, please reach out. I'm open to freelance projects and consulting. The full post is linked in the description below. Complete RLS policy reference, the 3-layer defense implementation, and the adversarial test suite. Next in this series, caching strategies, ISR HTTP cache control headers, and what I'd add with Redis. I'll see you there.